All attendees are in listen-only mode.
Hi, Kevin. We'll give the rest of the folks a few minutes to get here, but welcome back. We'll be going over some more OpenSCAD and if we get through all of the OpenSCAD material, then we'll start learning a little bit about Inkscape, which will help us add some cool features to our 3D modeling. So just give everyone else a little bit of time, just in case. That would be youngengineersoftoday@gmail.com. And I have some more information about that as well. It sounds like the specs on the design will be a little bit limited. Basically, they'll have to be fit into 80 millimeters by 80 millimeters by 10 millimeters. Hi, Gabe. Yeah, we were just going over. No problem. Sounds fun. Well, I'll get back to your question, Kevin. When, maybe in about 3 minutes we'll get started here. But you can both feel free to ask questions if you like. Also, I'm not sure if you got the email to download Inkscape, but if you didn't, then go ahead and start getting that downloaded. And in particular, if you have a Mac, there's some extra instructions. So if you don't have the email, just let me know. I'll make sure you get it. That's fine, Gabe. Yeah, we'll get started in about 2 minutes. Let's see, Kevin. Do you have a Mac, Kevin? Windows, good. Okay. Here, let me pull that up. Okay. So that's for Windows, and click on the first link. You'll see files available for Windows Installer MSI. That's the one you want. Right here. No problem. All right, we'll go ahead and get started then. So, OpenSCAD, we started, okay, yeah, let me cover some details first. If you have any questions installing Inkscape, it can take a long time. If it seems like it's just not responding, just leave it. Don't touch it. Don't hit cancel. It can take over 10 minutes sometimes. Just especially even the first time you open it, it just takes a while to load what it needs to load. So just let it sit in the background and don't touch it, and look at your computer. Just leave it and come back to it. And hopefully, that's the biggest problem. A level 3 strawberry garden, cool, Gabe. I don't know what that means. Three-story strawberry garden, cool. That sounds fun. Awesome. So, y'all probably want to know about what we're going to, what are the requirements for printing out your things that you've been designing, your 3D creations. So, Mr. Dubick has given me some specifications. Primarily, the size has to be 80 millimeters by 80 millimeters by 10 millimeters or less. Smaller is fine, but it can't be bigger than that because of the size of the 3D printer. If you really want to get something printed that's bigger than that, there's two options. One is if you can design it just one part being 10 millimeters tall, and then another part being another 10 millimeters tall, then you can piece it together that way and maybe super glue it together yourself. The alternative is there are, even through Tinkercad, you can't hear me, Gabe. Can you hear me, Kevin? All right. Well, Gabe, that brings me to another point. If you can hear me, I have posted the YouTube videos, every single one since we've started this semester. So I'll post a link for that, and today's lecture will get uploaded as well. So if you can't hear me, there's the YouTube link. All right. Yeah, and the other design spec, I guess, is that it has to be in Tinkercad, but there's a way we can get around that, and that is just, save it. Inkscape. Really? Well, I hope it's all right. Maybe, I heard that it was pretty process intensive. I'm sure your computer's actually fine, but it's always unsettling. Gabe, do you have a Mac? No, I guess you wouldn't if you built it from scratch. Okay. A Mac? Apple computer? No, good. Okay. Yeah, Mac is particularly difficult. You have to download another program to run Inkscape, so XP is good. So, yeah, we were talking about specs, 80 by 80 by 10 millimeters. If you want to get around it, you can print more than one thing at multiple slices of 10 millimeters. But you can only do 10 millimeters at a time, and you have to import it to Tinkercad. But we'll see that we can do anything. You can import anything to Tinkercad as long as you save it as the right file type. So all of the programs will work just fine. So I'm glad you got Inkscape downloaded. I'm not sure if you heard me, Gabe, but I posted the YouTube playlist link in the chat window. So if you'd like to check out, sure. There you go. That's fine. I'm glad you're back. So that's the playlist. You can also just Google search Young Engineers of Today on YouTube, and that will bring it up, and just make sure you click on the virtual section if you want to watch the sessions that you attended. You can also watch other people's sessions too if you like, I guess. It's perfectly fine. So we left off talking about transformations. So we you can do a lot of things for free, but you don't get to participate in the lecture. You don't get your questions answered, and it's not in a classroom. So that's part of the world we live in today. Is now what you're paying for is not necessarily the material, but maybe the structure and the organization. Yeah, well, as engineers, we like to do things open source, so it's nice to release your videos so that anyone who has the motivation to try themselves, they can teach their own. Free college is a pretty cool idea. I like that idea too. But back to what we've been talking about. I left you off last time with some translations to play around with, particularly translate to move stuff without resizing it, rotating it to change it around. Inkscape will, it's kind of like Paint, but much more powerful, and there's really one particular feature that I don't know very much about it, but I do know that it lets you do a couple of really, really, really cool things, which we'll get to hopefully at the end of this lecture. We learned translation, rotation, mirroring, and scaling. So pretty much how to move stuff around and change the size of it in space. So, yep, and we've got our cheat sheet. Translate, rotate, scale, mirror, they all take a vector, and that vector is how much you want to do that operation in the X, the Y, and the Z axis. The next question you might have is, well, we have these tools. Can we make anything we want? And yes, you can make any shape you desire. All you need is to provide some points, and you can make any straight line edge you like. So the paths work. Your points go in order. So you start off with, in this example, you've got points 0, 0, so your points would start here. The next point is 10, 0, so it's, 0 to 1. The 10 is along the x-axis. Then 0, 10, that takes you up to the y-axis. And then 1, 1 takes you here. 1, 7 takes you up. And 7, 1 takes you here. So that you just defined all of the points. But what's important now is what path does it follow. So you just have to know what order you put your points in, which you can see, and then you define it in your path. How would you like this to trace? And if there's holes, you have to include multiple paths. So it'll include the outer path and the inner path, and it'll know to treat those as separate objects rather than trying to connect the point between 2 and 3. You see there's no, because of the separation in the paths here. So that's how that works, and you can make, if you want to follow this example, you can make what looks like a triangle or some sort of ruler maybe, straight edge or square edge, or you can be more creative. Another thing we can do is make spheres. Would you guys like to see me doing this in Inkscape? No, Gabe, I did not, and that's because I was working on these YouTube videos. Okay, let's get this switched over. All right, so we're in OpenSCAD. We can do things like, one sec, sorry. Okay, so type in code, hit design, compile, and render, and there we have it. We've got a sphere. I wish it were easier to switch back and forth between applications to show you. Okay, so we can go back to our slides, and in addition to the sphere, you can add, oh yeah, oh shoot, okay. You can add, well, let's just delete the sphere, let's turn it into a cube. Cube, size, equals 10. Center equals true. Do you remember what center does? Center is particularly useful for understanding where your axes are. We compile and render this. Oh, you know what? Let's make this a lot easier and go into preferences. Oh, how did I do this last time? I forgot already. View, show axes. There we go. Look at this. So this sphere, let's make it bigger. That's pretty tiny. Design, compile and render. This sphere is centered, and it's centered right, you can tell it goes through the middle of the axis. So the center of the sphere, or of the cube, is in the middle, the axes go through the middle of the cube. Now what if we take out center equals true? Design, compile, and render. There we go. So now the first corner of the cube is where the axes meet. So that's important in remembering to figure out where to center. We'll see as we get more complicated objects. You might decide to choose one or the other to make it easier on your math. Another object we have is, gotta remember to switch using this program. Okay, we can do cylinders. Cylinder, H equals 10, R equals 5, center equals true. design, compile, and render. Okay, so here we have a cylinder. Now what happens if we what if we don't want to name it H? What if we name it hi or hello? Will that work? All right. So give me 1 second, Gabe, and I will do that. So what happened here? I call this hello, and it's still compiled and rendered, but it shrunk. Now what happens if I take it out entirely? Compile and render. Same thing. So in fact, if you don't use H, then it doesn't understand that's what the height should be. Exactly. So basically, it's as flat as OpenSCAD will make it. Let's go back to slides. Let's see. All right. So now this is interesting. So what if we want? Hold on, Gabe. I'm just downloading it now. I'm not going to go through this example, but you can, if you want to, instead of using R equals 5 for the same radius, you can do R1 equals something and R2 equals another something, and you can get a cylinder with two different radiuses. Didn't mean to open that. Okay. Let's see. Hang on, Gabe. I'm getting. Kevin, would you like me to email this to you too? Can you send me your email again? Is it? Yeah, okay. Attach. Where did this go? Here it is. Okay, so it's loading. It'll go. You should get it soon. Or it's uploading, I guess I should say. All right. So we've got a lot of shapes we can use, and some shapes even take different options. We've seen the polygon takes points, or you can also use points and multiple paths to make to cut out a section of polygon. Basically, it takes the first using the two different paths or multiple paths, you can include and exclude certain sections, or alternate including and excluding sections. Some that we haven't seen so far include text and polyhedron, which you can experiment around on your own. And let me check and make sure those emails that email got sent. Yep, it looks like it went through, and you should get it soon. Okay. So That's we've got our basic shapes down. Now, what if we want to do a little more experimenting, but we start getting, we're trying to add a bunch of shapes on top of each other. What if we want to put a dome on top of a cylinder and we want them to scale at the same time? So the way we do this is by working with variables. So we assign variables and then we use the variable like it's a number. In this example here, we can say A equals 10. We get our semicolon. We replace the H with an A here. And compile and render. And it's the same thing. So that's easy. Let's make it a little more readable though. Height and radius. Okay. What did I say? Radius equals, I already forgot what it was. 5. Let's do it. Okay. Now we can add a sphere. R equals radius. Let's see, what do we want to do? Translate. If we want to put this sphere on top, we have to go up in the z direction. So we go 0, 0, h, height. But height is centered right now, so height over 2 is how far we want to go up. And let's see what this does. Oh, I forgot. So there we go. Now what if we want to change the radius? This is the advantage. We get, let's make it much bigger. Radius equals 20. Compile and render. There we go. They both scaled at the same time by just changing one number, which is important because, we could easily change these two numbers, but what if we had 100 different objects we wanted to translate at the same time? We wouldn't want to change the number 100 different times. We just want to change the number once. So that's the advantage of using variables. Everything scales just when you need it to. So yeah, we can also make things, as this is showing us, this slide's showing us we can use the variables in math equations, basically just how I showed you. They're just a substitute for the number. So you can see here, I have to switch application. Okay. You can see here, you can definitely tell that there's this isn't actually a perfect sphere. It's not a perfect round section, and that's because computers don't work in not round sections. They work in a square-based or grid-based coordinate system, which is a Cartesian coordinate system, where everything is at right angles. So it makes it complicated to define circles. So how do we get around this? Basically we just up the resolution. So resolution is just the degree of sharpness. This what we had was a lower resolution. It's defining fewer points to connect this flat, and if we have, in theory, if you have infinitely many flat sections connected in the right way, we could have a sphere or a cylinder that is perfectly smooth. But that's only once you get down, so you can only see so far, so high of a resolution So once you get past that, ability to see or feel, or however you want to define your resolution, or your, however you want to you touch or feel or see the object, then once you can't notice anymore, then you're at a high enough resolution that it doesn't really matter, at least as far as you're concerned. It might theoretically affect some other properties, but basically what it means is, in this slide here, you can see here's a extremely high resolution chess knight, and you can tell definitely once you start getting towards the end, you can see, well, this last one's obviously not right because it's crooked and it doesn't even stand up straight. You can see it almost looks like it has some gouges dug out of it. But even this night before, I'm not sure if you can see once it's gone through the internet, but I can see even the layers that printed to make this knight a knight. And then, as you get to the last three, it's kind of hard for me to tell the difference. So I imagine the resolution deteriorates as it streams over the internet. It has to compress this image. So compression is another way of reducing the quality, but ideally at an acceptable amount. You also change the resolution on YouTube if you want to stream faster. You change the resolution down. If you want higher quality video, you change it up. And recently the MacBook, or Apple came out with what they called what did they call their screen? Retina screen. Retina screen display, Retina display. So what that means is they're claiming that their screen is at a high enough resolution that it is impossible for your eye to see any single pixel, because it's so close to that next pixel that your eye can't distinguish between those dots. And so, if what you're viewing has a high enough resolution, then you'll never see any pixels on this, Mac's Retina display. And they're not the only ones with it, but they might have been the first. That's resolution. So how do we change resolution? We add it as an optional parameter. Nicely done, Gabe. So let's do two steps at once. Let's say, I don't know if we can make this a variable, but we'll find out. Okay, so cylinder, cache fn equals, oh yeah, of course we can. So resolution, let's start it at 10. Let's see what that does for us. So we'll say fn equals, I'll call it reso, because that's too long. Okay. Translate sphere radius cache fn. That actually stands for number of fragments. So if we save this, compile and render, and you'll see, whoa, that got way worse. So what happened here? Well, the default resolution was actually higher than 10. There's more than 10 fragments when it builds this cylinder by default. So let's up it. Let's double the resolution to 20. See what happens. Okay, that looks kind of like we started at. Let's go 40. Compile and render. You'll notice it took a little bit longer to do that, to render that, because it actually has to do the math for every single one of these flat segments. But there we go. Let's see, can we get better? Let's try 100. Let's see what that does for us. Might have to go back see how fast this takes, how long this takes. Waiting, waiting. Now you'll notice there is a little bar down here that tells you your progress. It doesn't seem to be moving very much, but we're supposedly halfway there. Oh, there we go. So even now it's pretty difficult to tell. You know, if I look really closely, I can see some layers in there, but that's pretty smooth. If I were going to print that, I'd be pretty happy with it. So that's resolution. If you want to speed things up, definitely helps. Definitely helps to keep the numbers small, and wait until you have your design. You know, see, I compiled 10 resolution of 10. You know, as soon as I clicked it, it just showed up just like that. No time to compile because that's easy. It only has to do the math for 1, 2, 3 times 10, 30 pieces. When it had to do 100, it had to do 3,000. Figure out the math for 3,000 pieces and where they were in space. So that's the difference. And actually, it's more than 3,000 because it started breaking these up into smaller and smaller segments. So that's why it increases not just by if you double the resolution, it doesn't just double the time it takes. It might quadruple the time it takes because it takes that many more and more pieces. It might even be you might even have to cube the number of time, the amount of time it takes or something. I'm not sure. But this is a good example. So if I go back to 100 and I hit design, compile, and render. I guess it cached this. So this is an awesome program because it just cached the result and it already can figure out without having to do any math again. But I can't actually show you again how long it took. But this is an example of when you watch a movie, you don't expect to see any of these any poor resolution. People tend to think of it as a pretty low quality movie if they can. If your action, if your action movies, if they look like this, then maybe if they're being pretty creative and artistic, they can get away with it. But typically, movie designers make animations that are at above like the max, above the level of where we can see actually the definition between any given piece. So to us, it looks like the real thing, or it looks fluid. So so just seeing this here, this is a very, very extremely basic figure, and it took my computer about maybe 10 seconds to do a resolution of 100, where if I looked closely, I could still see the difference. So maybe if I upped it to a resolution of 1,000 or so, maybe I couldn't tell the difference anymore. That probably would take my computer maybe 3 minutes to render. And remember, this is still really simple. So when animators make animations in movies, that's why their animations take hours and hours because they have to render every single frame. Is its own separate image, every frame in the movie, and they have hundreds, if not thousands, or tens of thousands of objects in that frame, all potentially moving. It's an important subject. If you want to see something fast, though, make the resolution small until you've finalized it, and then up the resolution to make it look good. That'll save you a lot of time. This is what we just did. Okay, so these are the last three tools that basically makes OpenSCAD equivalent in what we can do, and maybe you might argue even more powerful because you have mathematical programmable control over what's created. But with the union, difference, and intersection, we can do what we did on Tinkercad. This is making holes, combining objects. So let's try this out. We want to make unite a cube and a sphere. So let's just go ahead and unite it with what we've got here. OpenSCAD. Let's go with, what did I say? Union. Nope. Open curly bracket, close curly bracket, and we put inside what we want to unite. So let's start off with a cube. A equals, what do we define a cube? Size equals 20. Size equals 20, and I will go ahead and get rid of this, just so that we can compare it to, just see the union operator. And sphere, size equals, let's go with, probably do center equals true, that's right. Semicolon, sphere size equals 25. Let's make this 40. Okay. Design, compile and render. And, nope. Okay, what's wrong? Union, it did not like the syntax. Am I doing something wrong? Oh, I missed a semicolon. Again. Okay, compile and render. Now what's wrong? Oh, I use size. R. Render. Does anyone see what I'm doing wrong? What'd I do, Gabe? No semicolon. Yeah, let's try it. Still doesn't like it. I am not sure. Let's see if it. Okay. Let's go back to the notes. I could have sworn this worked before. But there's no, I'm definitely doing something wrong. Union, open curly bracket, cube size equals A, center equals true, sphere R equals B. I replaced the variables with numbers, but that's fine. Okay. That slide had something missing. Okay, what did we do wrong? We forgot to give union, and in the slides too, slides are missing parentheses for the unions. So we need open close parentheses, then open curly brackets. So that's the union. What if we want a difference instead? Oh, hey, before we decide that, can we add another object to it? What if we want another sphere? Or cube, maybe. Cube size equals 40, center equals true, but we want to be able to see it, so let's rotate. And I forgot an exactly what rotate takes. So I'm going to go back and look at that cheat sheet. Rotate takes X, Y, Z. So we want to rotate in the, I guess it doesn't really matter. Let's go 45, 45, 45, all the directions. Let's rotate. Design, compile, and render. And yes, there we go. We've got a bizarrely rotated cube thing, cube spheroid. So that worked. Let's see what happens if we do difference. That's the next one on our list. Design, compile, and render. Oh, this is funky. So what happened here? It might help if we comment / yeah. Okay. Let's see what happens if we just do the first two. Okay, so this is very obviously a cube minus a sphere. So when we go back, what happens if we add more pieces? Well, we get a cube minus a sphere minus the rotated cube. So difference takes the first object and draws it, and everything after that it treats as a negative. It subtracts out that space. We can keep on subtracting out until there's nothing left, or not, because what's the point? But yeah, so that's the difference operator. Let's go back. Okay. Oh, and then intersect. So intersection, we'll go ahead and comment out our second piece again. Do intersection, see what happens. Okay, oh, look at this. So this is all of the places where both shapes had, contained solid space. Neither shape was empty in this location. If we want to go ahead and add back in our third figure, the fourth would do the, will always act the same as the third here. Keep subtracting off space, but the intersection you can think of as like a Venn diagram of shapes. So you can see there's a couple of spherical things. It's kind of like constraining it within a sphere, but also, those two cubes we stuck in there. Basically, this shape is never going to get bigger. With an intersection or a difference, you'll start off with, your first shape, and every successive shape will cut back on that material, whereas the union will build material, build two shapes together. These are mathematical definitions of intersection, union, and difference as well. So, because it's a math-based program, that makes sense. And just some tools. You can use stars at the beginning of a line to skip the line or disable the line temporarily. You saw I can also just like hit / to add a comment that I think does the same thing. Let's find out. Let's go back to OpenSCAD, hit star on the rotate, compile and render, and yep, it's just ignoring it. So it's basically like we commented it out. It's just, it helps you troubleshoot usually, when you get more complicated figures. If you want to see what happens when that line doesn't run versus when it does run, that's good. You can highlight it. Let's see what happens when we Compile and render this. It's supposed to show this in red, but maybe an intersection makes it behave weirdly. Let's turn this back into a union. See if that makes it behave less. Nope. Okay. Well, it's probably best not to use these inside of curly brackets. I guess that's what this means. Cube size equals 40. Not center it and run. Well, maybe read up on the documentation for highlight if you want to figure out how to troubleshoot using highlighting, because it doesn't seem to be working for me. And then let's go back. So you can also put an exclamation mark, compile and render, and what that does is only show that one piece, which is really helpful if you just can't figure out what is changing. So you know, say our design is really complicated. We've got a lot going on. We don't really know what this does here, or, what this means. We could make it smaller too, and it would actually be harder to tell. Let's see. Too small. 21. Yeah, so this blends in. It's pretty hard to tell that this cube is, what this cube is doing. So if we want to just see this cube, this is a better use case. Put an exclamation mark. You can see exactly where it is. Take it out. Run your design again, and you can see it's there. It's an alternative to just going ahead and deleting it with running it. Hitting Control-Z. Just a couple of steps to save you time, and help troubleshoot basically. Yeah, this is. Gabe said this seems complicated at first, but when you explain it, it gets easier. Yeah, so we're going to get into, well, this is what highlighting's supposed to work like. Maybe it's not working well on mine or something. I don't know. You can test it out and see if it works for you. It's possible it doesn't like having 3 pieces in there or something. I don't know. Anyways. Oh yeah, so here's a challenge. We'll end on this challenge. Yeah, give it a shot. And now try to say, oh, nope, I can't copy and paste because it's just going to hit I can't send the enters. Oh well. It's going to save you guys some time and type it myself so you can just work on the other sphere, but never mind. And if you like, you can add a screenshot of your finished product to your digital portfolio or whatever other things you like. Yeah, if you have any questions, just let me know. Oh, I think I forgot to mention for printing, that will probably begin next week, either Monday or Wednesday. And the way that'll work is when you'll send an email to Mr. Dubik at youngengineersoftoday@gmail.com which I'll remind you next week since we won't be able to do it until then anyways. And when you email him, then he'll know you're ready, and he can load it into the machine and have it ready to print. And then he'll send you an email back saying, whenever you like, you can start the print. And it's actually connected over the internet, or it will be, so that you can click run, and as long as nobody else is printing at the same time, but you'll be able to see in the webcam whether someone else is printing or not, you can hit run and you can watch your piece print when you click print. So hopefully that will work. I think they're still ironing out the last couple of details to connect it up. So they said it should be ready by Monday, I think. How are you doing on this, Kevin? I'm not trying to rush you or anything, but if both of you got it, then I'll be happy to move on. We still got 3 minutes left. Okay, yep. So basically, you need to figure out what shape you need, how big is it, where should it be centered, what axis, and in what direction should the shape be moved so that it's centered at the correct point. In this case, you've already got one dumbbell, so as Gabe pointed out, it's you really just need to change the direction on the axis and add that second sphere in at the change the positive to negative or vice versa, and there you have it. So that was take some creative thinking to figure out which number you actually need to change, but once you get down to changing, it's just copy paste and then make that one detail, change that one detail. So I think you'll tend to find that's pretty true of most things you do, as you incrementally get, go for harder and more complex things. Another solution would be to copy paste the same piece and then apply a mirror across the x-axis. It accomplishes the same thing, and there's really no, both ways are pretty equivalent. Some design points if you want to create something that has cool colors or to help troubleshoot, that sort of thing. You can just use the color functionality. If you look up the documentation, there's different ways of defining it. You can say green, but that only works for so many colors. So if you want to get the full color range, you can use 0 to 225 is red, 0 to 225. The next one is RGB green, and then the last one's blue, and then the fourth goes from 0 to 1, and that's opacity, which means you can make it partially see-through. 1 is fully opaque, so you can't see through it. It's the default. If you set it to 0, then it's entirely see-through, and you actually can't see anything. So I'll end you with that, so you can make some. You can actually, if you wanted to try to make a person, like a cylinder, sphere person, or whatever shapes you like. You could go ahead and try that, or whatever you like. Yeah, we'll get into repetition next week, but just have fun playing around, and remember for your specs, let's see, next week, I think I'm going to go straight into Inkscape and show you, how you can, Inkscape will really help us with, taking anything any picture we find on the internet and making a 3D version of it, or at least, partial, kind of a 2D, more like a 2D version of any picture we see on the internet, but make it so that we can print it in a 3D way. So I'll start off with that, and then if we have time after going through that, we will pick back up with OpenSCAD and learn some more tricks to make things a little easier. So with that, have a good couple of days, and I'll see you on Monday. I mean Wednesday, not Monday. Wednesday. I always say Monday. I don't know. Just if you know when you should come. Even if I say Monday, it's Wednesday. You always have classes on Wednesday too. All right. Have a good night.